Okay, so let us study about today's topic, the emergence of HDL. In the previous classes, we started with some of the introduction about Verilog HDL, including the history of Verilog HDL. Now the emergence of HDL here, what is the need of it? The need is to standardize the language for hardware description. The reason was earlier there was no special language for hardware, especially for hardware. Because earlier only for software only the language was existing. So for that reason, so they need to be standardized language for hardware description. It has recognized by IEEE, the Verilog and the VHDL language. Next, so now when you are writing some languages, the second thing is what you need to do. They need to verify the response, or I can say they need to verify the output of the corresponding circuit. So for that, later what happens, the simulators are emerged over there to verify the functionality of the circuit. Next, it can be used, it will given the path to implement the circuit. That is, just like the designers can manually translate the program into gates with the help of the EDA tool. As a designer, you have to think the designer means who is the designer? We are the designer. You have to think in that way only. So the designer can able to manually translate the programming into the circuit or gates, I can say. So later what happened, logic synthesis technology has come, so it is pushed the HDL into the forefront of digital design. Why? In the sense, later the logic synthesis tool has come actually. So this tool will give you the interconnection of the circuits, how the gates are interconnected. That only the logic synthesis tool will give. That has come in the late 1980s, dramatically the change in the digital design. Because when writing any program, say example already as I said, when you use XOR and OR, we know that how it will be. But when you're going to use the programs using the if statement, the case statement, or using the loops or behavior model, I can say, we cannot able to predict what kind of the circuit the system will generate, or we cannot able to know what kind of circuit will be there. So with the help of the logic synthesis tool, so we come to know what kind of circuit it will generate, or what kind of circuit it will convert from your program. So that can be happen. So we can design a register transfer level using an HDL that we shortly will call as RTL. The name as the register transfer level in the sense when you write some program that will be transferred to register level. Each and everything level will be register level. So that is why we are saying it's a register emergence level. So now the very simple the design flow here we are saying. This is a very simple design flow. We can see the left hand side which shows what are the levels will come in the diagrammatic way we shown. Right hand side what are the different will be there. See initially what happened. This is we can say. Yes, this one. So normally this one I can say is nothing but the specification we can say. So the specification in the sense this will be a specification, system specification I can say. Because if you want to design or if you want to fabricate one IC in the sense, initially what the people will give in the sense, they'll put some system specification. So based on that specification, you need to design the circuit. That is the question will be that. If I take with the concern about your analog circuit or which you studied in your linear integrated circuit, say I may say you have to design one amplifier that has to produce the gain of so and so. So now what you have to do, you need to design some circuit to produce that much gain. The same way I can say if you come for digital circuit, they may ask the question as like you need to design so and so the circuit which has to perform these are the operations. So at that time what will be, this is the one simple block flows I can say, this is the module actually. This one will be the module, these are all the inputs, this is the output. Now what you will do, this is the system specification. After that what you need to do, you need to write a coding. That is I can call as the behavioral description I can say. But you can see here architectural design. The architectural design in the sense once the specification is given, you need to design the architecture. Architecture of the circuit.
ನನ್ನ ಕ್ಲಾಸ್ ಇರುತ್ತೆ 11:30ಕ್ಕೆ ಸ್ಟಾರ್ಟ್ ಆಗುತ್ತೆ ಇವಾಗನೇ
architecture design. So that architecture design, once it is done, in the sense what you need to do, you need to either you have to write the programming with the help of coding. In the sense you can way two ways. Once the system specification given, the one the way is writing the program. That is, this is either VHDL or Verilog, I can say either VHDL or Verilog. This is the one way we can do. The another way is what I can say, in the sense that is the another way you can draw the schematic circuit. The schematic circuit of the specification you can draw. That is the other way. So now you think in this way, you return the Verilog HDL code. Once the Verilog HDL code is written, still we doesn't know whether your code is correct or wrong, whether performing properly or not. Still you doesn't know.
Black code.
Yogananda, please shut and close the system. If anybody else want to talk, please leave from the class and talk. No problem. So once you return the coding, so after that we doesn't know whether that program or the coding will be will give you the proper response, or it will give you the correct output or not for the specification which you return the program for the corresponding specification. How we come to know? So you need to check. So how we can check? To check, we need some simulator is required. So further, what you do? You have to use some simulator. With the help of the simulator, you can perform the functional design. That is called as functional design, or sometimes they may call as functionality verification. We may call. So functionality and the logic design. This logic design will give you nothing but what? The logic design will give you the interconnection between the gates. That is the interconnection, how the one gate is connected to another gate. See here we are showing. Once we return the program, next it will translate into the circuit design. See here it has translated. Okay, once it is translated to the circuit design, next what happen? We'll go for the, we need to place. This is the place, in the sense example we are going to use the circuit that is called as, we are going to use the circuit, or we are going to use the board. PLD is nothing but FPGA we are going to use. Example. So if you use a FPGA, so in this what you need, it is a ready-made available chip. So if it is ready-made available chip, in the sense, what will happen? You assume like this only. Example I will say, see, see, now you think this is your chip. So now in this chip, I will assume like this. Okay. See, my chip is, now you assume this is my chip. Now what happened? This is the partitions. These are the partitions. You need to place your circuits. Exactly where exactly you need to purpose. For example, if your logic circuits are having very less number of gates, I don't want to keep in this place. So what will happen? The system will automatically, it will take in which location it has to place. So automatically what will happen? After that is, I can call as place. So your circuits will be placed on the board by automatically actually. So once it is placed, next what will happen? From one gate to the another gate, it has to be done with the wiring. That is called as route. So that is the name I can call as place and route. Place and route they will call. So we need to perform the place and route. Once place and route is done, next here you can see something newly they mentioned, that is nothing but a physical design. This physical design is nothing but where we'll do in the sense, if you're not writing the Verilog or VHDL program, if we go for the another method, that is nothing but schematic. If you go by this way, then what you need to do, that is nothing but your circuit design. See, this is the programming level, this is the schematic actually. Just together we are putting here. Next is physical design. So what will happen once the schematic circuit is drawn? Next we need to draw the layout. This is what we can call the physical design is nothing but drawing the layout of the schematic diagram. Once it is done, next what you need to do, whether you draw the layout properly or not. You may think, what is layout? The layout is nothing but it's a geometric representation of the layers. In the sense, layers in the sense you can say you might have studied CMOS, whereas a design we studied. In that fabrication process we studied, as well as we done schematic and layout. I hope, sorry, the people who are not studied CMOS well as a design. Okay, so what you need to do, you need to draw the diagram, schematic diagram. Once you draw the schematic diagram, next you have to draw the layout. The layout will show like this only, like the circuits are with the geometric representation, like only the polygon shape, square shapes and rectangle shapes only will be there. So that only we need to draw with the different colors. Why? In the sense, finally when you're going for fabrication, the who's going to fabricate our IC, they will come to know what kind of diagram we drawn, because we are going to use their technology only. Here one thing is, I can say, in the physical design, something called as technology. In the physical design, I can call something called as technology. Technology will based on nanometer design. Nanometer, micrometer, like this will be there. Now I will say technology in this, technology nanometer in the sense, now at present, not at present, I will say example, what are the nanometer, like 180 nanometer, 90 nanometer, 45 nanometer, 22 nanometer. Next, again called as 17 nanometer. Next, 14 nanometer. Next, 7 nanometer. Next is 5 nanometer or 3 nanometer. Example. See, now what happened? Gradually, this is nanometers are specified. This is length of the channel. This is the length of the channel. The sense, example I want to show how it will be in the sense. You have to assume in this way. Let me take example. You assume like this, okay? So now what you will do, you have to assume in this way. Let me take example. You assume this is nothing but a one mass. Example, just this is example, okay? This is the one mass. So in this mass, you think you studied, remember your MOSFET? This is nothing but a source and drain. Example take. This will be nothing but your length of the channel. You studied in your basic electronics or your analog electronics. This is the length of the channel. This length of the channel only I will call, this is L. This L only is nothing but this measurements which I specified here. So now gradually what happened nowadays, this size length of the channels get reducing. When the length of the channel get reduces, what will happen? Automatically the electron movement will be very fast. Then the performance also will be very fast. At the same time, the size of the transistor also will get reduced. That is a very important. That is what we are going to take care here. So next, what you need to do, you need to verify the design. That is we can call as physical verification. So after that, what we'll do, we'll send for fabrication. You can see here in the physical verification, we'll do these things. DRC, design rule check. LVS, layout versus schematic. ERC, electric rule check. So these are the verifications we'll do in the physicals. Then after that, we have to send for the fabrication. The fabrication, this is nothing but a silicon wafer. This is the silicon wafer. So once it is fabricated, next what you have to do, we need to do packaging and we need to testing. Very, very important here, one thing is said. Before fabricating, we cannot modify your circuit after fabricating. So very, very important. So whatever the correction if you are doing, that has to be done before the fabrication only. Else all the total cost will become as waste. So you have to be very, very careful. That is the reason what you are doing. We are performing the simulation in different levels. We have to do the verification. That will show in the next. What are the different levels of verifications are there? Once the fabrication is over, then we'll go for the packaging and the testing. The packaging in the sense IC packaging. You might have studied. One of the example, if I want to say DIP, that is dual in packaging. You might have studied how it will be the packaging dual in normally which you used in your labs. Those all are dual in packaging only. It's like the pins will be in only these sides and this sides will be there. But if you see in your mobile phones or any other board in the digital signal lab or any other previous board, you might have seen like this IC also, like quad flat pack in the sense all the four corners pin will be there. That is QIP they may call. Okay, but here this is the one package, this is another package. So that is we can call it as packaging, and we need to do the test. So that is testing is nothing but we need to once the packaging is over, again you have to do IC testing. You remember, right? So that we have to perform. Testing has to be done. Once testing is done, then we'll go for the chip. So is finally the chip will get like this. That is why the initial process will start from here. Next, this is the one method that I can call as top to bottom methodology. That is called as top to bottom methodology. If we go by this way, then this is nothing but it is like bottom to top methodology. Like from the circuit, from the fabrication to, from here you have to go from the fabrication, to, if you go in up, that will become as bottom to top methodology. This is top to bottom method. Two different types of methodologies are top to bottom, bottom to top methodology. The same like one of the little bit expansion level of that. This is what we explained in the previous case. Now, this is the one of the very, very important question with respect to your examination. Keep it in mind. This is the one of the very, very important question. In examination, they'll ask, at 90% you'll get. Now, first thing is typical design flow cycle, or sometimes we may call it as VLSI flow cycle. We may call like that also. This is what diagram. This diagram we need to draw. So like what are the steps which will involve here? Design specification. Then behavioral description. Then RTL description. Functional verification and testing. Logic synthesis and timing verification. Gate level netlist, logic verification and testing, floor planning, automatic place and route, physical layout, layout verification, implementation. Now you can see here they are having two different of typical design flow which merged here actually. In the sense in this we are having two different design flows there. One is nothing but which are the portions are shaded here. That is the shaded block shows the process in the design flow. Which are the shaded portions are shows the process in the design flow. The unshaded portions, see, these are the unshaded. You can see these are all portions. We specified here. Unshaded block shows the level of abstractions. The level of abstraction in the sense we are having totally 4 different types of levels of abstractions are there. That is data flow modeling, gate level modeling, behavior modeling, switch level modeling. Those things I can say as unshaded. Sorry, I can say as the different levels of abstraction levels. Now, let us see here how we can explain these things. Initially, as I said earlier, we have to start with the design specification. The design specification already, as I said, it is like the design specifications are written first. So it describes theoretically the functionality, interface, and the overall architecture of the digital circuits to be designed. So now at this point, the architects or the designers need to think about how they will implement this circuit. They have to think how they are going to implement. So further, what you do next level is behavioral description. A behavioral description is created to analyze the design in terms of functionality, performance, and other high-level issues. Now the behavioral descriptions are written with HDL language. Behavior descriptions are written with the HDL language. Now the new EDA tool have emerged to simulate the behavioral description of the circuit, because once you write the coding, still now we doesn't know whether our program is correct or wrong. How will you come to know this is right or wrong? Until you cross check or you need to verify the output. Once it produces the correct output based on your input, then I can say yes. So we can say this is a correct program only. So further, what happened nowadays, it has emerged. The new EDA tools are available. EDA in the sense electronic design automation tool, that is EDA. EDA tool is nothing but electronic design automation tool. So electronic design automation tool in the sense, already I said which and all. Example is Xilinx, Cadence, Synopsys, Mantra Graphics. These are some EDA tools actually. So we can use any one of the new tool, but in our college we are having Cadence is there, Xilinx is there. Both are available in our college. So now once it is done, what you will do, the one more important thing, these tools, whichever the EDA tools we are having, it has the powerful concepts in the HDL and OOPS, that is object oriented language. Examples such as C++. So it can be used to, instead of writing the behavioral description in Verilog HDL, the sense it is not meant you need to write only the Verilog HDL coding, even though you can write the OOPS const based on the program also, that I can call it as system C program. Nowadays, recently it has come. What are the language and additional language in the sense? We can say system C. Example, I can say system C, system Verilog. See, these are some additional new languages now we are having actually. This system C for design, system Verilog is for use for verification actually. Here, next thing is what we can say, in this behavioral description, once you return the behavioral description, it will manually, it will convert to the RTL description in an HDL. So the designers has to describe the data flow that will implement the desired digital circuit. So from this point onwards, from this point onwards, the design process is done with the assistance of EDA tool actually. So now next what we have to do, we have to go for the RTL description. The RTL descriptions manually convert to RTL description in an HDL actually. So here the designer has to describe through the designer. The designer has to describe like the data flow that will implement the desired digital circuit. In the sense, they have to think in which way you can write the program. You can choose. So from this point onwards, the design process is done with the assistance of EDA tool. From there, from here, it will start the reality using the EDA tool actually from here only. Because until here, we'll do everything will be done in the manually. In the sense, this is the creating a architecture, developing the architecture from the specification. Then we need to write the coding also. Once we return the coding, then we need to perform the simulation also. This everything we have to do manually. After that only the system will do everything automatically. That is one of the very good feature in the EDA tool. We can perform everything automatically. So now in this we are having what we'll do once the program is written. Next what you need to do, you have to perform a functional verification. What is the functional verification? The functional verification will verify the functionality of the design. Very, very important. It will verify the functionality of the design, whether it's a response for a given input or not. That we'll do up to here. This is the simulation purpose, I can say. This is nothing but simulation. You can see the arrow mark here. Once this is not giving properly the answer, you see the again what you have to do. You have to go back to your program and you have to recheck whether it is there like it is properly written or not. So again you need to check the functionality. Once the functionality is done and once you checked, verified and tested, next you have to go for the logic synthesis. So what is the logic synthesis will do? The logic synthesis will convert the RTL description. The logic synthesis will convert the RTL description to a gate level circuit. The RTL description in the sense I can say software or program you can say that will be converted into hardware circuit. That is what I can say gate level netlist. That we can call as synthesis they may call. The synthesis will generate the netlist. That is the meaning of that. So during the synthesis there only will perform a timing verification. So this synthesis, logic synthesis will tell you or it will give you how the gates are interconnected in the logic synthesis. The logic synthesis tool will ensure that the gate level netlist meets timing, area and power. See here which one? The logic synthesis here. This will ensure the gate netlist meets timing, area and power, because once if you are going to design any circuit in VLSI, three parameters are very important parameters. That is I can call as the we can call the speed or I can say the timing of the circuit, whether it's meeting the with the proper timings. Then area, what about the area of the circuit? Next is what about the power consumption we can say. So these three parameters are very important when you are going to design any circuit. So now during this time only, so we need to think whether it should, the logic synthesis tool will ensure that the gate level netlist meets the timing, area and the power specification. The gate level netlist is an input to automatic placement, where you can see logic synthesis. Then what happened? Gate level netlist has come here. You can see gate level netlist. Next, after that, what will do? Logic verification and testing. This is we think problem. Logic synthesis. This is logic verification. Logic synthesis, we can see here, there is a logic synthesis and logic verification. The logic synthesis, as I said, it will convert what? It's a tool actually, it converts the RTL description to gate level netlist. The logic verification testing will be like we need to verify the logic, whether it's meeting the timing, area and power specification. That is what we'll do here, the logic verification. Once it is done, we can see here, if we are not meeting the timing, area and power here, again what you need to do? You have to go back to the RTL description here. You can see this arrow mark. See, so this is the second level. I can say this is the first level. This is the second level, the testing of your circuit. So once it has to meet, if it is not meeting properly, you have to go back here. Next, after that, what it will do? Next, the gate level netlist. This will be a input for floor planning, automatic place and route. The floor planning, this is the what it will do. The system will do automatically. This will do. So the floor planning and the place and route. The circuits will be placed and it will be routed properly. Once it is done, next automatically what will happen? We'll go for the physical layout actually. The physical layout what will happen? This is as I said earlier. This is the another one more process. Like physical layout is nothing but what we may call as physical design, or we may call as layout design. This place we can call as layout design. This one we can see once the layout design layout is drawn. Next is layout verification. We need to perform the layout verification. Then you can see here one more very important. We can see layout verification. If it is gets failed, again what we'll do? We'll go for the third testing level. That is nothing but here. It will check for floor planning, automatic place and route. So at the same time, it will check for what? It will check for here. See, wherever you go, you have to come to the RTL description. That is, which you written the program. There only we need to come. Once it is properly layout verification is done, then finally I can go for the implementation. So that implementation can be done in the sense finally we can take out the final IC chip. So you need to think the DDA tools for this very important thing is essential. The tool is what? It is a DDA tool. This will help the designers to convert the behavioral description. So here, from here to IC. Finally is, I can say, final IC chip. Final IC chip, I can say. That is the very important thing. This is about your design flow cycle. This is one of the very important question for your examination.